I have no comment on this. I didn't know about this, and I hope we shall proceed quickly as possible. Okay, so today we're going to study the Maxwell stress tensor, and after studying this, yes, you'll need 1 hour break for sure. You need to dance and enjoy life.
When we talk about the Maxwell stress tensor, we talk about the relative ones, the Maxwell stress tensor, or the classical one, Maxwell stress tensor?
What is in this classroom is actually the classical one, but it applies also for relativistic case in the sense that the electromagnetic fields can be relativistic.
Yeah.
So I'm following Griffiths. It's the Maxwell stress tensor.
Of the classical one.
Yeah, I don't know exactly what you mean by relativity because there is
the F mu.
That will be in the last lesson. Okay, now I understand what you mean.
Because you have two types of something called the electromagnetic stress tensor, Maxwell stress tensor, and they both code this way, and they are both different things. So I want to clarify.
Okay, so the one that you are referring to will be taught in the last lesson. The last day of the semester, this F, you mean F nu. Here we are talking about what is usually called T, which is more related to things like pressure and shear.
Yeah.
But the fields don't need to be classical. The speed of light is in there, so I don't call this classical in the sense of relativity. But let's just remind you where we are in the course. So, okay, so now we are in chapter 8, and we are discussing the stress tensor. Other parts of chapter 8 were already discussed previously. Part of the course is conservation of momentum. So the stress tensor, as you'll soon show, as I will soon show you, we will be able to calculate, let's say, forces on bodies, which are charges and things like that. And then, of course, if there is a force, then there is a Newton's law. And if there's a Newton's law, there is a conservation of momentum. But in electrodynamics, this is a conservation of momentum between the mechanical momentum and the electromagnetic momentum. So this I'm not so much teaching, but you have to read and know. What you don't need to read, but it would be nice in this chapter, is conservation of angular momentum. So this is optional if you want to read it. I'm not teaching it. But this is these two things are part of the course. And again, I'm going to focus on this one, and you can read this. This is only one page in Griffiths. I think it's easy enough, and go ahead and just read it. Yeah, in chapter 9, so we already studied, we already covered a lot of it. But part of what of chapter 9 was covered in the homework. For example, waveguides. Okay, so waveguides is part of homeworks. For example, Fresnel's law, Snell law. The reason why I don't teach it in class is obviously I don't have enough time, and secondly that I think you study these things in other courses like optics or maybe electricity 1, but they are certainly part of the course, because in Griffiths they are kind of, for me, you have Maxwell equation and they are solution of the Maxwell equation, so the Griffiths maybe gives you a new perspective. So it was given in the homework assignments, etc., but you need to know it. I'm not saying you don't need to know it. The thing that you don't need to know in this chapter is I mean, it would be nice if you did read it, is, yeah, this frequency-dependent permittivity. It's not covered in this course. So I write here optional, not part of the course. Then next week we study chapter 10. And if this class is a little bit complicated and full of algebra, then the next one is even worse. So you should read chapter 10. It's a very important chapter if you want to prepare yourself to the next lesson. And today I'll give you, if I have time, I'll give you I'll point out what are the type of questions we want to ask in chapter 10. Then chapter 11 is radiation, and chapter 12 is your F mu nu. That will be the last course. Okay, so this is what we're going to do. Next lesson will be 10. Then the following one will be radiation, and all these things are related to relativity, and all these things are slightly more complicated in some sense than what we had up till now in the course. So yeah, it's a good time to start reading is now, if you didn't do this up till now. Okay, so now I want to start the lesson, and unless you have some questions. And I want to teach this stress tensor. So what is our goal is, okay, stress tensors. The way I present it, it will be the following question. We want to calculate the force of the body. Very, very classical point of view. What is the force on a body? Of course, if there is a force, then there is an acceleration, there is a conservation of momentum, etc. This is what I mentioned before, that I'm not going to discuss the momentum. I just say I want to know just the force. And what do I mean by this exactly? I have a body. This is my physical body. I have in it charge density, and maybe I have some currents in here, and maybe I have currents out here, and maybe other charges here. And these currents outside some sources create electromagnetic fields, which might be time dependent. So there is some electromagnetic fields here, and then I want to know what is the force on this body. That's the question. For that, a mathematical tool is the stress tensor, but this is not only a mathematical tool, it's a really deep physical insight. It's also used in other fields like general relativity, etc. So the stress tensor is very important. Also, the word stress, what does it mean? It's a kind of pressure. So because the electromagnetic fields have momentum in them, or energy, so you are creating stresses, pressures, and shears, as I will show you later. So this idea of tensor exists also in relativity, also here, but also, let's say, in continuum mechanics of bodies. So it's a very general object that I'm teaching here in the context of this Maxwell's stress tensor. So what is the force on this body? This is some arbitrary shape. Of course, usually we cannot calculate it. So we can calculate, let's say, the stress tensor, then we need to solve things numerically by integration if this is going to be a complicated body. All the examples here will be very simple examples that you can solve in other ways. You can solve this problem, let's say you have two charges. Okay, I know how to calculate the force. For example, in a static problem, I just use Coulomb. We can solve it in other ways. But the stress tensor is a more general way, and it contains in it information. Usually, this is not the only unique way to calculate the force. So the question is, what is the force in this body? And this force I denote by capital A, F. So what do I need to do? This is my body, and I have here some element, volume inside, and on this element volume there is a small force Fi. So there's a big F, which is the total force, and there is the small f, which is the force on some part of the system. This will depend, maybe I'm going to delete this. The small f is, there's of course one force here, there's another force down here, etc., or on the surface. And how do we calculate the total force? Well, we need to sum up all the forces. This is a vectorial summation. And if I can sum up all the forces, then I'll get the total force. Okay, this is in principle the mission. This is obvious for mechanics, and this is what we need to do. Now, this small f, it's not exactly a force. It's the small f is going to be a force per unit volume, as usual. This is force per unit volume. It's not exactly pressure. Pressure, for example, it's not a vector. We will soon see that there's different types of pressures. It's not totally wrong. If you said pressure, it's not totally wrong, but it's not totally right. It's more than that. So this is F, and it depends on X, Y, Z, and T in principle, depending on the sources, currents, whatever you have here. So what we need to do is we need to sum up the forces, okay? Okay, but we know the answer. Here is the answer. What is the answer? The F on this body is the sum over all the forces. So let's write the sum. What is the sum? The sum is an integral, right? You know that? So let us write it in here. It's some elementary, this is a sum over the volume. And we are going to write it, and this is E plus V cross B. Times what? Times the charge, right? E, that's the electric field. B is the magnetic field as usual. V is the velocity field at each one of the points, multiplied by the charge density times d tau. D tau is the unit volume, like in Griffiths. That is why I taught you for the first half of the course what is d tau. So I think this integral is very clear. And what we are using here, this is simply dq. We are just multiplying the charge with the E and V cross B. So this is elementary, this is high school physics, right? This is what you know, and everything is good. Okay, so, and this is what I said before, that in simple cases that are solvable, you can use this equation in principle to calculate all kinds of forces, and you did it many times. But now we are doing a different method, using this complicated tensor. Just, you know, as usual, we like to complicate things. No, not really. We're going to complicate. So what is the idea here? What do we need to know in order to calculate this force? I need to know E, B, the velocity, and rho at all points inside the body. That's quite a lot of information. Maybe we can reduce it to something that depends only on the surface and not what is happening in the body. Maybe I can get rid of some of these symbols. Let us start thinking about it. Which symbols would you like to get rid of? Or that's what's Maxwell's idea, to get rid of them in this equation. Let's get rid of V, and let's get rid of rho. For example, you might not know what is rho inside the body. Now, let's look at rho. How do we get rid of it, rho? What is the idea? How would you get rid of it? If you are Maxwell.
You can replace it by using Gauss law.
Exactly. So this is the general idea. Rho I'm going to soon replace by Gauss' first law, div E equal rho, with this epsilon 0. Right? And what is V? V, especially V times rho, what is that? That is the J. The J, the current. So then I can use Maxwell Ampere law from Maxwell's equations. And then I can replace them, and then I'll get something. But the problem is, I'm going to do that now. The problem is I'm going to get a mess. And then we're going to tidy it, like bookkeeping, like boring accountants maybe, and then we'll get the stress tensor. But that is the idea. Reduce the four fields, if you can, to E and B only. That's the general idea. And start playing with this and see what happens. But before doing that, let us think a bit what advantage, at least one advantage of this approach is the following. Which type of problems would we like to solve? Let's say we have the body like this. This is the body. And let's say I managed to replace E and B, rho and J I got rid of. I think you understand more or less that this is possible. Maybe ugly, but possible. Now I have the body. What I can do, in some cases, I can change the integration volume to locations where rho is equal 0. So let's assume that here there's no, there might be far away some J and rho and whatever you want that are creating the electromagnetic fields. But let's say in this box there is none. There is no J here. There might be rho and J inside, of course. You need rho and J inside, otherwise there will be no force. This is when the force. So you see that I can extend the integration F body in this case, and let's write this body, it looks like that. I'm integrating over the body. I can integrate now, let's say, over this box, and now I'm going to put it like this. Why? Because rho is equal 0, I can extend the integration. Okay? Then I'm not... this by itself is a small thing, I mean, but I don't need to go and do this integration over a complicated boundary in principle. I can go and integrate over here. The price is after I replace V and rho with E, I need to know the fields all over the place, not only in the body, right? Because this is integral d tau. Now, if I can also show if that I need only the boundary and not everything inside, and this will be at the end with some divergence theorem. It will be possible to do integration over volume, you change integration over surface. Then I'm very happy, because then in this case I can integrate over this part, and then if I know the fields here, I can calculate the force on this body without going inside the body, without knowing anything on the body, without etc. So these are the general ideas that we want to explore now. Okay, more or less this is the some aspect of this issue, but it's much deeper than that. Okay, so let us do this and do the math. Okay, so this is our equation. Maybe you should take your notebooks and write it like that, because the equations are going to be sometimes long. So, okay, so let us first of all define what I call small f. Small f is simply what I have here. You see, all this is force per unit volume. This is an element of volume, so this is force per unit volume. This is at a given point, x, y, z, in a specific point inside the body. So this is what I call a small f, E v cross b rho. That is the definition of the force. But now v cross rho is what we called j. This is just a reminder that is, in the body there is some movement of velocities, otherwise the magnetic fields will not create any force, right? So there is a velocity field at point x, y, z that creates this j, this current per unit volume. This rho carries with it the charge. So this f is simply, I want to write it like, okay, rho times E plus j cross b. And this is what I'm going to work with. Now I'm going to use Maxwell equations. So I'm going to call this step 0. And then in step 0 I'm going to write down, or simply, what is rho. Rho is simply, as usual, given by Gauss' law, as mentioned already. It's given by this. So this is Gauss, which is actually Coulomb. We know the density. And then we want to calculate the current, which is, again, this is the Ampere law corrected by Maxwell, but I'm just rearranging it a little bit. Usually the source is on the right side and rotor B is on the left, but now I'm just changing the order of the equation because I want J and this is rotor B. This is the usual ampere divided by mu 0. And now comes the Maxwell's correction, which is dE dt. So the first step is going to insert J rho in small f. Okay, this is straightforward, and let us write it here. Maybe I should delete it now. Let's do it. Small f. Later we will integrate, but now, again, we are looking now at something very local in space, at point x, y, z. Later we need to integrate it. It will be horrible, but okay, we will be able to do it, or Maxwell was able to advance it a little bit. Div E, how do I want to write it? Times E. So what is this div E? The div E is just the rho, right? This is just the rho. And I write it like this. This is a vector. F is a vector, so this is a scalar. And this E is a vector, so this is what it means. There's no dot here or anything like that. And this is rotor, just copying this one. Rotor B divided by U0 and minus E0 dE dt cross B. Cross B. This is simply this one, and this is, of course, just the J. So, okay, so we didn't do too much, but this is already a slight, we went one step forward and two steps backwards in the following sense. We have here B, E, and O, rho, and J. Good. But we do have here time derivatives, and we do have here rotors, so we don't need only the field at the point. We need the, you know, all these rotors, all this div, and all this stuff to get things. And then there is now there is another issue. So this object is not symmetric, or it doesn't appear symmetric with respect to E and B. And physicists love symmetry for good reasons. So now what we are going to do, again, following Griffiths actually, we want to symmetrize this. We want everything to appear in the same way for E, the electric field, and the magnetic field. To tidy this up, this is what we're going to do now. And this, we are going to do some simple tricks. Okay, so what are the simple tricks? So let us look. We have this from the Maxwell's corrections to Ampere's law. We have this dE dt cross B. Okay, so what we will do, we see here a multiplication of E and B. So we're going to take the time derivative of E cross B, and then a time derivative of a multiplication of two functions is, you know, the chain rule. You need to subtract both. So I just write it down, and I think it's very clear. This is d dt E cross B. And then there is a small issue that why do we have a minus sign, but this is a trivial issue. E cross B dB dt. Usually you are used to that this one is on the other side, you put this on the other side. So this is a derivative of multiplication of two functions. Okay, it's a cross term. And then you have the derivative of the first E, and here you have the derivative of the second function B. And because it's a cross, you get here this minus. Yeah, okay, if you put it on the other side, it will be trivial. But what is this dB over dt? What is it? Yeah, that is, Mr. We should remember what, when we are advancing, this is minus rho, and this is Faraday. This is the way I want to say about it. So along we are using Maxwell's equation. We used already Gauss law. That's one. There are four equations. Here we are using Faraday's equations. Here we use Ampere. What else is left? Div B equals 0. That's the last one that we didn't use. We should remember, we better use all of them. Otherwise, I mean, it's reasonable to use all of them and not some of them. So here I'm going to use, okay, so here I use Faraday. So let us write it, just tidy it, dE dt is d dt E cross B, and this one will be plus E cross rotor E. So again, this is Faraday, really. Faraday. Now, along this awful exercise,
לצד שמאל שלה.
thanks. So along this exercise, we need to, or most people need some encouragement. Why do I like this E cross B? What does this remind me? Something has to pop up, pointing. And this is related to flux of momentum and with the time derivative, which is a concept that you can understand intuitively. This is related to forces. So we are very happy with this. And this is what I said before. This is what I call a symmetric term. E cross B, okay, it could be B cross E, but they are treated on the same level, E cross B. Okay, but what did we do up till now? We just treated this one, right? And here, now let's look at this E cross this thing. Here we have a similar term, rotor B, so it's similar to this one. So we are starting to tidy things up. I think you can see it, but there is no equivalent to this term in B. I can add it. Why? Because div, here I have div E, which is raw. If I add the same term, but with div B, but that's 0, I can add it. It's free, something for free. So for symmetry, I'm doing something silly. I'm adding a 0, but I'm creating a symmetric theory with respect to these two fields. So we have here div E, this is this term, E, what about B? So div B, this one is actually 0, and now I used all Maxwell's equations. Up to now I already used all of the 4. This one can be added for free because it's 0. Okay, so if I put all this together, there is one more trick. And this is the following trick, and you can tell me why I would like to use this trick. Well, there could be, for different people, different reasons. I have this term.
With minus and move the E.
You can switch the order of the...
Let me say what I want to do, and then you will tell me. I can switch the order, I can do many things, but that's mathematics. What did you say? I just want a word. I just want one small word. No, that's math. Maxwell was a physicist, not a math. Okay, let me write it down, and then you want to say? Okay, I'm just going to write this in the following. This is a mathematical statement. I'm not going to prove it. I'm not going to be, but you can say maybe why this step is a bit worthwhile for a physicist, maybe not for a mathematician, because it's an identity for a mathematician. So why do we like to write this like this? At least one of the terms is kind of saying, hey guys, look, there's something interesting here. The square of the E is not energy. I mean, it's the energy density. And what are we calculating? Just remember, we are calculating force. So it is related to energy, like potential energy. The derivative is related to force. So if we have here the energy density, energy per unit volume, that's a good thing. And we can do the same for this term. Sorry, not for this term. Where is it? This term. We can do the same, and then we'll have B squared. And B squared is also the energy density. This was taught in the previous class, and then we are slowly bringing in some concept of energy, relating between energy and force, which is kind of what we expect, and now we get the following equation, and then this will summarize everything up. How should I write it? It's very nasty. At this stage, it's very nasty. Well, it's always nasty. Okay, so this is F. If I summarize all this up, I have epsilon 0, div E times E. Again, this is Gauss, this is rho times E. This is, I think, obvious. Then I have E div E. This comes from this term. And if I didn't mess up things, the minus here will be without the minus, this minus here or something like that.
With the minus down.
Yeah, you can see it better. I'm too close to the wall. But this is the same. And okay, and here what will I get? I'll get 1 over mu 0. I get div B, which again, this is 0. And unlike the rho that is here, B. And here I have B dot B. So, of course, you see here the symmetry between E and B. We managed in our minor, or not minor goal, to symmetrize the expression as far as we can, and to write everything in equivalent terms. Understanding, of course, epsilon 0 and mu 0 are different, but that's a minor story. Then I'm going to write the second term minus half the derivative of epsilon 0 E squared. E squared is E dot E, and here I have mu 0 B squared.
Why did you
Symmetrize?
not why did you symmetrize? למה מחקת את האחד?
Because here I wanted to write it like this, but then I changed my mind because of my hand. That's the reason. So, okay. And, okay, the last term is d dt, E cross B. And here I have this epsilon 0. And then we can, this is a final expression. This is not the stress tensor yet. So what is this guy? This is pointing. And here you have the time derivative, which is different. Here you have, this one is rho. This one is actually 0. What is this? This is the energy density. Vector pointing, we already discussed it a little bit, is carrying the momentum. So here is like a change of momentum of what? Not of the mechanical momentum of the particle. That will be F. If you integrate over the force, then you'll have a change of the momentum. This is Newton. A change of the moment. The total force is equal to the change of the mechanical momentum, right? And this part is of mechanical momentum of the body, and this part is the momentum of the field coming out here. This is rho, and okay, all the rest, this one is 0, and all the rest are a little bit more math, but the important thing here is the symmetry between E and B. Okay, so we have this equation, and this equation is still pretty disgusting. But now we're going to, we're going to introduce a mathematical tool, which is tensors, to write it in a more elegant form. But actually, this is it. This is the answer, and then we're going to further tidy it as far as we can to get the stress tensor, and then we need to understand what it means, which you will not understand everything in this class. This you need to think about the stress tensor. It's very complicated. So what is Maxwell's stress tensor? This is a definition. It's Tij. Tij means the following: the Maxwell stress tensor is a matrix. It's a matrix which is a 3 by 3 matrix. We call it tensor. Why do we call a matrix tensor? Okay, I'll discuss that later, but this is the question. But for you now, let's say this is a matrix. What is I and what is J? I is X, Y, and Z, and J can be X and Y and Z. So this is a 3 by 3, actually symmetric matrix, and with real entries inside. So this is a tensor, symmetric matrix, real. Every such tensor is a symmetric matrix, but not every symmetric matrix is a tensor. It's not the same thing. Okay, and what is it? Let's use this as definition part of this board. Tij is the following nice thing. It's epsilon 0 ei ej minus half delta ij ei ej. Remember, the I and J are indexes X, Y, and Z. They can be anything. And you have here another term, which is, okay, expected because of the symmetry, 1 VU0, BI, BJ, minus half delta IJ, BI, BJ. Good morning. So this is the Maxwell stress tensor, and you see that is a 3 by 3 matrix, but it's a very special matrix in the sense that it's a matrix, but at each point in space and time, which is 4-dimensional X, Y, Z, and T, it can change, because these fields will change in different positions. So it's not just a set of 9 numbers. It's a 9 numbers, which each one of these numbers is a field of X, Y, Z, and T. But that's not the reason why we call it tensor. But it's a complicated object. Delta Ij, I think you know this, is the Kronecker of the delta of Kronecker. This is equal 1 if I is equal J, that is, let's say, XX or YY or ZZ. Otherwise, it's 0. Now, up to now, this was just a definition. I just put it on the board. I didn't show how you use it, etc. This one? You have 2 indexes. So this matrix is, for example, TXX, TXY, TXZ, etc., right? And you continue this. We will have this soon on the blackboard. I'll explain it. But every object with 2 indexes, I and J, run from X, Y, and Z. So you have here. So for example, let us answer this question. Let us see. What is TXX? What is TXX? This is a diagonal term. This is one of the diagonal terms. There are off-diagonal terms which have one physical meaning, and diagonal terms which have a different physical meaning. These diagonal terms, I'll soon show you, are like pressures. The off-diagonal terms are like shears. Okay, start thinking, what do I mean by this? And I'll soon give shears, gzira. Shear, I don't know. Yeah. Well, I'll soon explain it, but let us look at the math. What is TXX? This is like this. Okay, let us do it. This is epsilon 0. I just need to put the index X here and X here. This is EX. Okay, let's write it like this. EX minus delta Ij. Here it's X and X. This is 1 minus half EXX. That's good, because 1 plus half, even I can do that. And then you have 1 minus mu 0. I don't see, do I want to write all of this?
No, that's just.
Wait. This is wrong. I made a mistake here. This is E squared. This is a very bad mistake. Don't tell the president of the university you will reduce my salary. Okay, so minus, let us see what this means. This is the total E and the total B. So this is minus half EX squared plus EY squared plus EZ squared. Plus the same for B. I'm not going to write it. Now here I have EX squared and here I have minus half. This is what we can easily do, and then it's easy to show that this TXX is epsilon 0 EX squared divided by 2 minus EY squared minus EZ squared. Again, these are E in the direction X, E in the direction Y, E in the direction Z. All of them are functions of X, Y, and Z in time. Yeah, so I want to put it here. Yes, thank you. I want to put it outside. Plus 1 over 2 mu 0, and you can understand the rest by yourself. So this is this object, for example. It's not it's not something that you are. It's a bit of a mess at this stage, but it is what it is. This is this TXX. Okay, so now. I just defined this. I didn't relate between T and F. Now I need to do that. I'll first give the statement and then I'll quote unquote prove it, but I'll not prove it for all the elements. I'll prove it for some of the elements, then you will feel why this is correct. Okay, so first of all we need to define multiplication of a matrix, and this is something you know, by a vector. What will be the vector eventually? Does anyone have a guess? This is the T. This is like the pressures. You think about it as a pressure. You need to multiply the pressure by some element of it will be area at the end, but okay. And this will be the vector eventually from physical point of view. But now let's just define what is a multiplication of a vector. So first of all, we are going to denote this is the stress tensor. Again, this is just a matrix. So this is a matrix, so the stress tensor has these strange vectors in two directions, but this is just notation. If you don't like that, I don't want to write T, because T is a scalar like rho. So this just means a tensor. You have two directions of this thing. And for example, this has an element in the J direction, and this is simply the sum over AI Tij. And we are summing over I is equal X, Y, and Z. So what is this? This is just multiplication of matrix, but there are actually two when you do exercises. You can multiply it from the left and you can multiply it from the right. You need to pay attention which side are you multiplying, but this is the usual thing. So everyone sees this is just the multiplication of a matrix by a vector. I think it's clear, right? This is just a definition. So what is the statement? So in this equation, I differentiate between the pointing vector here, which is a time derivative on all the rest. So I have here 1, 2, and 3 terms. These 3 terms are related to the t in the following sense. Yeah, I'm going to write this. I'm going to leave this equation. This, I don't know what I hope it's not a handkerchief, but okay. So I'm going to write these important equations. I'm going to write here because maybe we'll come back to them. And this is the main equation. This is the relation. F is the divergence of this T, epsilon 0, mu 0, ds, dt. And this is essentially, this is the force. And again, the force is equal to what? If you want to look at it dynamically, this is the force that enters into Newton's equation in the electromagnetic field. What is S? S is simply the vector pointing so what do we have here? We have here this matrix. You have the div. So what is this reminding us, or at least it reminds me? This is a kind of a potential. The T acts like a kind of a potential in the following sense. How do you derive F in high school? It's the derivative of some potential. Here you also have a derivative of some object, but it's not a potential. It's much more complicated. It's a stress tensor. And remember that in general, this is a bit surprising because the first part of the course was always saying, you know, if you have time-dependent fields and all these things, you don't have a usual potential, things like that. You need a vector potential for E and things like that. Vector potential A for calculating B. But now to get the force, eventually we get this stress tensor, which is a generalization. In this word, there is an issue with the sign, but that's just definition. And then there is a second term, so this is momentum loss due to time-dependent field. Like you can think about it like maybe some kind of mass change that, you know, the derivative could change. And all this is equal to the field. So this is the statement. What is this force F? Now remember, this small f, this is more or less, we are in the middle of the journey. This is the small f. To get the big F, we need to integrate this. And this we will do soon. But now we first need to understand why this F and this T, given by this relation, why do I claim that this guy and this guy are the same? T is the matrix, which is, don't call it matrix, maximum tensor. T is the tensor, which is a matrix. And you see here that I defined here this object. So this object you need to replace here with div. And then you will have here J will be x, y, z. And then for the force F in the x direction, you'll have one element where you have here this Jx. In the y direction, you'll replace that here with y, etc. This is what we're going to do now. So this object has a direction in the x, y, z plane in some reference frame. So, okay, it's clear. So let us do exactly that with one example. Yeah.
What is the rank?
This is if I remember, this is rank 2, but
Like 0, 2?
I don't. What do you mean by the 0, 2? Or the
There is like,
I don't know. The answer is I don't know. I don't know this notation. It's 2, but if you are talking about the number of invariants or something like that, I don't know how many invariants. I know 2 of them, but I don't know if they're all of them.
Okay.
I'll talk a little bit about the invariants later. Yeah, this is. I guess you learned some mathematical course, or I don't know the answer to this, but there are some invariants. The invariants are, just to elaborate a bit more, the main difference from my point of view between a tensor and a matrix is that a tensor does not depend on what reference frame, in some sense, you are working in. But it's a bit complicated because this tensor, will it depend on the reference frame? Yes or no? The answer is yes. The tensor the elements of the tensor depend on which reference frame you choose. And this is easy to see. Imagine you have a situation where the field, let's say there's no B, there's no time dependent, and you have a field in the Z direction, and then you switch it, and then it's in the X direction, then of course you're going to change the elements of the matrix. So different reference frames have different representations of the elements of the 9 elements of this object. This sounds pretty bad, but when you will plug it into the calculation, let's say, of F, and then average over the F in the right directions, then it will not depend on the reference frame. That is the idea of tensors, which we are not we're not elaborating on this, we're not proving this, but this is the major difference between a tensor and just a matrix, a symmetric matrix which doesn't pay attention to the reference frame. So for me, the word tensor implies some deep physics independent of the reference frame, but not for the elements themselves, but for the results of the physics that we eventually get. For example, in the calculation of the total force in some direction, it doesn't matter which reference frame you work at. Okay, but that is going a little bit too deep, a little bit too far. Let us just show that this and this are the same for one element. And let us look at, for example, on small fz. So now I'm choosing the z direction. There are 3 directions here in some Cartesian coordinate. And yeah, and okay, so first assume, for simplicity, b is equal 0. We're going to throw it away because everything is symmetric. This is okay. What is Aleph? Yeah, let's call this one Aleph. And let us calculate, first of all, with this f, and then we'll calculate it with this object. Let us calculate what is fz. So there's b equals 0. This term goes away. This term goes away. This one goes away. So we are left with 3 terms. And we want to look at the z direction. So fz is the following. It is epsilon 0 so you see here div e, so I need to take all the elements, and then what are we going to take for e? Because I want fz, I'm going to take ez only. So this is the following. This is d dx ex plus d dy ey plus d dz ez. This is simply this div e, which is, what is this? This is simply the density multiplied by ez, because I have here z on the other side of the equation. Plus, now I'm looking at this term, e, so I use Aleph. Okay. So E div, so what is that object, this nice object? This is Ex ddx plus Ey ddy plus Ez ddz. And what E I need to use here? I need to use here Ez. And again, Ez depends on x, y, and z. And let's say there's no time here. That is this minus, now I need to take care of this one. So here, what do I need to take? I need to take only the derivative, because I'm looking at fz, only the z derivative now. And so now I'm taking only the z derivative. which is this epsilon 0 over 2 d dz ex squared plus ey squared plus ez squared. So, but what do we claim? And we can check it. We claim that fz, what is fz? Now we need to use, let's call this is bet, and then gimel. This one is gimel. I need to replace this general vector A. I said before it will be an element of an area, but now it's not an element of an area, it's this div. I need to replace it with this and look at the z element. So from this gimel, what do I get? This one is equal to the following. You see, these are derivatives now, and this is simply d dz tzz plus d dy tyz plus d dx txz. This is just a definition. Well, I'm using both this one, both B and Gimel, to find the definition. And this is just a claim. I need to check that this one and this one are the same. So what do I need to do? I need to use this equation now with the definition and see that we get the same thing. Ooh. Okay, so use the stress tensor. Let us see what will happen. Okay, but this is too difficult. So what will we do? We will look just on the terms that depend on the derivative with respect to z. I mean, you can do everything. I mean, Maxwell had a lot of energy. So let us look at the derivatives with respect to z. I have here a term. I have here a term. And I have this one. We will have other terms where we'll have all kinds of derivative with respect to x, but you'll have to believe me, or you can do it yourself, that the two formalisms are the same. Now I just look at 3 out of the, we have a 1, 2, 3, 4, 5, 6, 7, 8, 9. So we look at 3 out of 9 terms, but there are other terms, but they will not contain derivatives with respect to z, they will have derivatives with respect to x. Okay. You can do it. I'll give it to you in the exam. No, not really. This is too bad. So let us look what this is. Yeah, well, we had here let us look at this. רגע, רק שנייה, תראי פה כי אני מתבלבל. E0, ddz, ez, this is from this term, times ez, plus E0, this is this term, and now this is this term. Yeah, this term is multiplied by here. It's the same term, that's the point. Ez, dez, dz, minus epsilon over 2 ddz ex squared plus ey squared plus ez squared. This comes from here. And then, okay, again, there are many more terms which depend on derivatives of dx and dy. But these two terms are the same, so if I tidy up here, this one is epsilon 0. You see here, this one plus this one, these are the same. I can write it as, okay, let us do it a bit slow, then I'll write it like this: 2 times half d dz ez squared. So what is this 2? These two terms are the same. And then I write it, this is the derivative times ez, I write it as ez squared. Why do I do that? Because here I have the square also. So I have the same term, minus epsilon 0 over 2 d dz ex squared ey squared ez squared. This of course makes you very, very happy, because this goes away, and then I can write this in the following way. It's epsilon 0 over 2 derivative of ez squared minus ex squared minus ey squared and then there are all kinds of terms with dx blah 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 and dy blah blah blah. But what is this thing? This is the stress tensor, but not all the stress tensor, of course. This is the ZZ object. This thing is the ZZ object, which we had it before, and you calculate it here. Again, there's no B, and you can see it from here more or less. You see that this is the TZZ. And this is exactly the claim that we have here, that the term with the derivative with respect to Z is the TZZ term. So including this part is exactly the TZZ. So this is equal to dz TZZ plus ddy blah 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 plus ddx blah blah blah. And if you calculate the blah blah blah, this will be this term and this term. So I just showed you here by just brute force calculation that this formulation and this formulation are the same. But why did I bother? Yeah, now you have questions.
In the first line of FZ down to the second one.
This one?
Yes, to this one. Where the epsilon 0, we assume the Ez dot E, the Ez dot Z is 0? No.
What again?
The second term. Where is
this
it?
one?
Yes.
Where did it come from?
No, where are you going at the second line?
To this 2. I just said...
But there is a 2 and a half.
No, yeah, but when you take the derivative, the 2 will cancel. There are two 2's. When you take the derivative, the 2 will go out here, will cancel this half, and then you'll get one of these terms, and then I multiply by 2 to get 2 of these terms. It's very easy to see. Again, it's trivial. Epsilon 0 Ez dEz is equal epsilon 0 d dz epsilon z squared over 2. And you have 2 of them. So I multiply by 2. It's very simple. I mean, you see this? Take the derivative.
אבל הראשון הוא אחד מהסוג הזה. כאילו זה לא...
But you have here 2 terms. 1, 2. And they are the same. This term and this term are the same.
Okay.
That's why I multiply by 2. Okay, so what we proved again, we proved that, we nearly proved, we didn't do all the steps, but Maxwell proved that this object can be written in a much more elegant form than this F with this stress tensor, and this gives you the F. Now we are not completed yet the problem, right? Because we need to use this F in order to calculate the total force. But now the trick is rather, I wouldn't say easy, but maybe now easy after you learned physics for 2.5 years, I need to integrate this over a volume. And integrating of a derivative over a volume is relatively simple in the sense that every time I integrate over something which is a derivative of something else, usually I can solve these integrals. If it's a simple one-dimensional case, this is the integration versus differentiation, the simple relations, but here it's a bit more complicated because they are vectors. Okay, so we need to use the divergence theorem, but this is not a big deal. Let us do this and see what we get. And there's nothing to get, but because use the divergence theorem. Okay, so what we do, we want to calculate now capital F, the total force on the body, d tau small f, integration over all the body, use divergence theorem. So with the pointing vector, unfortunately I need to integrate over all space, but for the stress tensor I just need to integrate over the surface. So doing that I get the following F using the divergence theorem. This is the, which is T dA integral over the body, right? But remember, this is the body on which we are calculating the force. But now, if we can extend the integration, as I mentioned at the beginning, we can extend it a bit more to regions where there are no charges and there are no currents, no sources of the electromagnetic field. So this integration y, you remember this, right? Because I can do that. You cannot see it here, but you saw it at the very beginning. Because the integration was over rho, I can change the integration not to include any charges. So maybe here, any box where the body is inside, you can do the integration, where again, only inside the body there are charges and currents, and here there are none. You cannot include charges inside. So these are the integration domains, which are super important, because in practical problems, if you want to solve things, you don't integrate over the complicated body. In fact, in many cases, imagine you have a complicated body here. You want to calculate the force. And let's say this body is in the middle of the sky. You don't know what are the fields there, but you can have, if you have a very big box around it, and let's say you can measure the electromagnetic fields far away from this body, you do know the values of the fields there, and then you can calculate the force on the body, which is rather neat. So this, what is the integration domain, is super important, and then the final result here is you have epsilon 0 mu 0 s, and here I need the volume. So this is d tau, again, integration of the volume, and here I have dt. This part I cannot avoid the integration over the volume. However, if the problem is static, there is no time dependent, then I can throw this away, and then I'm left with this one. And this is what we do now. We assume they're going to use one simple example where you are static, and later, I mean, this S is super important, the Poynting vector is for dynamical problems where you have radiation and things like that. But for a class of problems which are static, then we can have this, only this term, and then, as I mentioned already, again, this dA, what is this dA? We have this body, and we have some dA. It's normal to the field. We need to know only the stress tensor not inside the body, on the surface of the body, that's enough. Somehow the forces added up in such a way that you only care about the stress tensor on the surface, and then again you can go further away if there are no charges and integrate over here. get the force. That's pretty nice. So let us But now, what is this T? What is this T? What is its physical meaning? We call it a stress tensor. I mentioned it is related to pressure, and I mentioned it's related to shear. So, pressure, intuitively, you know, let's say this is a balloon. Then you have a balloon. There's some pressure inside. It pushes the balloon outwards. I mentioned in some analogy, this will describe the diagonal terms of the stress tensor. And what is shear? So imagine you have a box, and inside there is a gas. So what happens is the gas is heating, so there's only concept of pressure that you studied in high school, right? But if you can take this box and you can do the following. You can shear it, which means, let's say this is the upper plate. You can push it in this direction, and maybe the down one, you can put it have pressure in that direction. So I can have a force in this direction and a force in that direction, or only on top you have a force in one direction. That is a shearing force. You are tearing it, you are stretching it. When you have a gas inside this box, there's no such thing. The gas just creates pressure. But electromagnetic fields are different. They also create this shear. And these are related to the off-diagonal elements. And now let us discuss this and see this more explicitly. Why do I claim this? What is the meaning of things? This comes from the definitions, from this definition, in fact. So now I'm going back to the small f. I'm looking at a small a point in space, and I'm looking at this f, and this is related to this this f eventually. The local f, the integral over it, gives you the big F. So this is like adding pressures, but again, it's not only pressures, it's pressures and shears together. So let us see this. So first of all, what is this? Again, T, this is just a sharpening of the definitions. This is simply given by this object, epsilon 0. I'm just using the definitions. Div E, Ej. It's essentially the same as what you have here, right? Plus E Ej minus half dj E squared. Plus magnetic terms, which I'm not writing. This comes from definition, if you want, bet, aleph, and this one, let's say gimel. It's all the same. Assume there's no time dependence. Assume statics. So again, F is this equation here, vector, this tensor dA. So let's start with the statement. The txx, tyy, and tzz. So let us look at this equation. What does it say? You have this equation, okay, there's a multiplication of a vector by a matrix by a vector. This, by the way, comes on the right-hand side, not on the left-hand side. What does this tell you? I divide this matrix into diagonal terms. These are the diagonal terms. Diagonal. And then if I have, for example, txx multiplied by dax, that is like, from units point of view, that will be force per unit area times area, and that will be like a pressure. I think you can see it from the equation. So these are local pressures. Force per unit area. What do I mean by local is simply that these functions, they all are at one given point in space. So it's not like pressure on a wall, or you can say the following. If I have a wall, I have the global pressure, which is in the equation of state of the gas, but on each point of the wall there's the same pressure. Here it's more complicated. On each point of the wall there are in principle different pressures. So this is a function of x, y, and z and t, but still it's a pressure, but I add the word local to it, indicating that it's not a global thermodynamic quantity. Txy, tzy, etc. is off diagonal. They have the same units, again, force per unit area. And these are called shears. It's also a force per unit area. And what do they mean? They mean the following, and I'll explain it more. So Tij, I is not equal j, is a force in the I direction on an element of area in the j direction. But what is this element of area? This is in this integral, this element of area. So on the real body, it's some element of area like this. So this is the element of area on a body. For example, let's say we have a real body which is maybe a sphere, and we have here an element of area, something. And this goes, let's say, in the g direction. Let's call it x direction. This is j direction. The force is in the I direction. So this is the direction of force. So you can imagine a sphere, there's an area, you go there, and then you have a force up. Even for a sphere it might look crazy, but it's not at all. Even on a sphere you can have a force upwards. Why? I didn't say at all what are the sources of the field. So maybe here there are some charges that are creating the electromagnetic fields. So why shouldn't there be a force upwards? Of course there should be upwards. It's not isotropic, the problem in general. If you have an isotropic problem, yeah, you expect the forces only from symmetry to go in these directions, but in general you have these forces up. Now, imagine you have another point here on the other side, and let's say in an example the other force goes down, so you have this kind of shearing, you have like this ball, and one force is going up and the other one is down, and that's shearing, for example. Or one of them is fixed and one of them is going up, you are applying a force on the body. It's not a trivial force that you are used to, but because we are talking about an object in 3 dimensions, it's not a point particle, you have this type of shearing effect. In principle, the force can be upwards, it can be outwards, it can be in all directions possible because of different configurations of charges outside, and that's why we need this matrix. That's the reason, a very simple reason why we need this matrix and we need this force here. To make this sinking a bit more, why do I say this is the force in this direction? Let us do a simple exercise. Again, looking at this one. So, what do I mean exactly by here, or how can you see it from the equations? You can easily see it from this equation. We'll simply use some examples. So, what is T dot dA? This enters into the integration, right? What is this object? Oh, let's think about it. This object is the following. This is Tx, Txy, Txz, Tyx, Tyy, Tyz. This is Tzz. This is Tzzy, and this is Tzx. And this is DAX, DAY, and this is DAZ. This is this object, like it or take it or leave it. And again, all the fields come inside here. It's not a nice object, but it is what it is. Now let us assume, for pedagogical, okay. Of course, we can write it also a more elegant way as like this: sum over the j, Tij, Daj. Notice that this is again a simple multiplication of matrices with a vector, but now the vector is on the right before it was on the left. That's just the change of the definition. The sum over j, as usual, is the sum over x, y, and z. So again, this is just the same thing as we have here. Now, let us, to understand the physical meaning that I mentioned here, if it's not clear, I just want to relate between this physical picture and the mathematical picture. Just let us choose, very simply, some directions of the volume, of the element, and see what it means. I mean, so again, what is this thing? This thing, TdA, is the force here, the small force. Eventually, yeah. So let us say, for example, say as an example, that dA is simply dAx times x. So what is T dA in the x direction? So what in this example I have an element along the x direction, and that's it. Say the end of my sphere. I want to calculate also what is the TdA, which gives you here, again, it gives you eventually, when you integrate over the surface, it will give you the force at this point. What is this one? I need here dAx, this is 0 and this is 0. What will it be? Txx times dAx. This is dAx, the area. And you see, What? No, because this is 0.
That's Ux.
I multiply this and I look only in the x element. So this, and this, multiply this vector, but here these two are zeros.
It's the sum of the
Txx, dAx. This is only the x direction element. Only the x direction element. So I'm happy you asked. So it's not so totally trivial, but you need to get used to it. This is the point. So this is only the x direction, and there are others. I'm going to discuss them, but this is when this guy is in this direction, and I'm looking at the x direction. So I'm choosing the two directions, and that's why only Txx enters, and that's exactly my point. So if this is a force on the left, because I calculate again with it the force, then this is the pressure. Because this is the force per unit area, and this is the pressure as usual. But if dA, for example, is dAy, which means it's a totally different object now. I mean, I'm just assuming that I'm looking at a different point, if you want. So now I'm looking at this point. I have a dAy. It's going in the y direction, right? And now I want to calculate, I will not calculate the force in the y direction also. It's the same thing as I did before, right? Now I'll calculate the force, let's say, in the x direction or the z direction. Now what I need to do is, my element dA is 0, 0, and then when I calculate the x direction, what will I get? What is T dA? But in the x direction, Txy dAy. So this is in the x direction. This is direction of this local force. You see here the off-diagonal term entered, and this means the interpretation is what I said before. I multiply these two things, and then I get the force in the x direction, because here I have x. So this is the force dAy is in this direction, and this is the force when I multiply, again, the force, I mean multiplication of these two objects in that direction. So now you see through a simple math, just by some simple examples, what I said in words, why I call this shear and this I call pressure. So this was the pressure, and this is the shear. Okay, so what is your verdict? You're going to abandon me? What is this thing for 1 hour? I don't think, I didn't hear about it, so I'm going to ignore it. So you want a break now, or are you going to go? I mean, I just want to understand what's going on. Who decides about this thing? I never heard about this. Yeah, but what, there are some elections, so they want to show you that they are nice people. Yeah, okay, they want to bribe you. But there was a Students' Day, no? Or today is the Students' Day? Yeah, the Students' Day is well known. So, okay, let's have 10 minutes break. I hope you'll come back and I will continue. Hopefully we can finish a little bit area so you can have beer, and then when you go to the... Some of you have 12, or you have exercise, I think, right? No? Some people.
Yeah.
Okay, so don't drink too much beer. Let's have a break, and then we'll have an example to use these equations to solve a very simple example. So what I'm going to do now is, and I'll try to be a bit fast because yes, there was going to be a party soon, and I want you to enjoy life. So maybe I'll skip a few lines and you can ask me later if you're interested in the details, but Actually, the two items I want to say now are more conceptual from my point of view than mathematically really complicated. So what I'm going to do now is a very simple problem. I have here, this is going to be the z direction, and this is the xy plane. And I have a charge here, q, and a charge q here, and this distance is a, and this distance is a. This plane is absolutely nothing. It's just a plane that I put here. And what we are going to do is we are going to do something which is beautiful, but also stupid at the same way. I'm going to ask, what is the force of this, that this charge, for example, is feeling? And you all know the answer, because this is Coulomb's law, right? The distance between these two charges is 2a. And you can calculate this, so of course I'm not going to... So what am I doing here? I'm doing something called sanity check. I have this complicated formalism, and every time you have the complicated formalism, the first thing to do is solve a trivial problem and see that you didn't make a mistake with the stress tensor. So what is the strategy? I'm going to use this plane. I'm going to calculate the stress tensor in this plane, t, x, y, etc. And then what? Then I'm going to use this equation. So what is t here? That will be our goal. And why is it easy? First of all, there's no magnetic field. And also the problem is totally static. There is no ds, there's no Poynting vector that is changing in time. So I need to calculate the E here, and if in this plane, and if I know this, the second final step would be the following. I know the T, then what I'll do, I need to calculate this F, right? Which again is the Coulomb force, the usual Coulomb force. What do I need to do? I need to integrate over all this area, and then I'll close it, let's say, from the up, because this is an area. So the idea here is the following. Remember what we said last class? This integral is over the surface of the body, right? But I said you can have a different surface as long as there are no charges inside. Why? This came from the fact that when we wrote it at the very beginning, we wrote the formula, it had contained rho times E times V cross B, right? And then I said you integrate over the volume of the object that you are looking at. But if rho is outside here 0, I can integrate over all this space. So I'm going to calculate the stress tensor here, and then I'm going to close the volume. You understand, this is a plane with a half sphere on top. Now, what do I need to do about the half sphere? Do I need to calculate the stress tensor there? The answer is no. Why not? This is trivial. Why not? So I'll ask you, why is it not needed? What happens to the stress tensor up here?
Cancel out.
It's zero because it's far away. It's simply 0 because you see the stress tensor depends on these E's. We have here two charges, and at infinity there is nothing. So what does this problem teaches us? First of all, we will practice how to calculate the stress tensors. Okay, that's important. But also it will teach us that if I know the stress tensor here, I can calculate the force on one of these charges. And this, from what I believe is an experimental point of view, is not totally stupid. Because imagine you have a charge, imagine you have a platform where with some needle, for example, in a lab, you can measure electromagnetic field, but only in a plane. You cannot go up, or you don't know, and even maybe you don't even know that there is a charge here and a charge here. But you can measure this here. You can measure the electrostatic field here. Okay, let's say you know that the field up here is 0. You can calculate the force on the object that is up here without really knowing what is the electric field, the electrostatic field really close to this object. But of course, this is not needed. I know exactly what is the electrostatic field in this problem, but again, we are using this very complicated formalism, and the advantage is I'm not really close to the object, and still I can learn something on the force indirectly. And again, if there is a limitation on the measurement devices, of course, if I put here a force meter, I will know the force. I don't need this. But if I have only this information, I can still get the force. That's the idea. Okay, the question is clear. I think it's a simple question, and you are anticipating the answer. So what do I need to do? I need to calculate the electric field in this plane, right? So this is what I need to do. And this is easy, I mean, because these are just two charges. So the two charges are the same sign. This is also important. So what is the z direction of the force, of the electric field, sorry? It's 0 from symmetry. It's not up, and it's not z. So I'm just talking in the plane, Ez is equal 0. So what am I left is with the calculation of Ex and Ey. So if this is z, then x is in this direction and y is in this direction. Let us calculate this, and it's very easy. So let us just plot it. So I'm using now only one charge, and I have the plane. This is the distance a, and I'm looking at some point here. What is this? This is r. So my reference frame is just here between the two charges in the middle. That's a common sense choice of the reference frame. I can choose the other reference frame, but that will be totally stupid. So this is the origin, and r is a radius inside the plane to some point in the plane. Now I can continue this a little bit. Let us define this angle as alpha. Then this angle is 90 minus alpha. This angle is 90 minus alpha, right? I mean, this is simple algebra. So, and then we also have, let us write it again. In this way, we have here A. This is the point A. This is the, how do I want to write it? This is a very bad drawing. This is the plane I'm interested in. Bad drawing, t minus alpha. Now I'm adding one angle, which is phi. So this is r. This is phi. This is just the usual definition of phi in the usual coordinate system, x, y, z. So what I need to do is I need to calculate first the electric field in the r direction, and then I need projections in the phi direction. This will give you cosine phi and sine phi as usual. So there are two, the bottom line, there are two angles. One is alpha, this one is 90 minus alpha, this is phi, and you need two projections. First you project it up, but that you are not in the x, in the whatever x and y is, then you need to project it to x and y with cosine phi and sine phi. I think this is clear because this is elementary in many exercises. So what is Ex? So Ex is, again, is the 0. Ex is the following, Q over 4, the famous 4, pi epsilon 0. What do I need? I need the distance here. So if this is r, this is a, this distance is r squared plus a squared. It's an electric field, so it's a square as usual. And here I need to write cosine 90 minus alpha, and then another cosine phi x. And what is EY? It's the same.
But sine.
What? This is just from one of the charges. Yeah, the sine. Okay, I thought you said I made a mistake with the sine. The cosine remains because you are projecting with it upwards, and here I have sine phi, and this is in the y direction. So what is cosine 90 minus alpha? I look at this angle. This is simply r over, oh, the party began. R squared. R squared plus a squared, right? Because you see here, this is r, this is the Pythagoras, this is smaller than 1. Unlike Donald Trump, who likes to dance. So this is this cosine, and then let us write Ex. Oh my God, now you hate yourself that you didn't go out. Good fun. Q over 4 pi epsilon 0. R. We are at X. So we have R squared plus A squared. This is to the power 3 over 2 multiplied by cosine phi x, right? And the same for y. I'm not going to write it, but you see where this 3 over 2 comes from? It comes from the definition of the cosine 90 minus alpha, and then you can easily find it. Now let's go. Okay, this is all well known. I mean, this is easy calculation in high school. Let us now turn it into a stress tensor. So what is Tij? Just let us write it down. Epsilon 0 Ei Ej minus half delta Ij E squared. So first of all, let us look at Tzx. I claim this is 0. Why is this 0? Because Ez is 0, exactly. Ez is 0, the off-diagonal term is 0 because of the delta. And here I'm left with x and z in this case, so z and x. But Ez is 0, so this one of them is 0, so the other one is 0. And similarly, Tzy is also equal to 0, and I want to focus now on Tzz. This is very simple. This is half epsilon 0 times Ez squared, but this one is 0, minus Ex squared minus Ey squared. Now, in this Ex squared and Ey squared, we're going to use sine phi squared plus cosine phi squared is equal to 1. So when I square these two objects, I'll get a square. The other part is the same. You see this? It's the same. So it's very easy to calculate this, and let us write it down. Okay, I can just copy this. And then I have Tzz. So I can find easily Tzz epsilon 0 over 2 q 4 pi epsilon, all this squared. The square is obvious because the Tzz is a square of the electric field, right? multiplied by minus 4. The minus comes from here. Okay, the 2 are already, yeah, they are these 2, but they are 2 fields. You need to check me. Yeah, okay, the minus 4, sorry. This is a field from 1 charge. But here I'm already taking care of the 2 charges because I have 1 on top and 1 on bottom. This comes from here, so this comes from 2 charges. All these numbers are going to be important because eventually in the Coulomb law, the number in front is going to be important. And then I have here r squared, it's essentially this one, r squared plus a squared to the power 3. So when I square this, I have r squared plus a squared. But I need to square it, so this is the stress tensor. Ooh, what does it mean? In the z direction, there's only kind of pressure in the z direction because of the symmetry of the problem. The other ones are not important. Now, I'm not calculating the other elements. Why not? So let us look at this. I'm calculating Fz only. Now you can say, that's not fair because I know the answer, but if I didn't know about these 2 charges, maybe I would also calculate Fx and Fy. But from symmetry, it's obvious that if I have a charge here and a charge here and nothing in between, the force is in the z direction, right? So you can use the other t's, all the stress tensors and integrate, you'll get 0. And here it's even more obvious because what is dA? We have here dA, right? And let's say I want to close it like that. So what is the direction of A? It's going to be downwards, and I integrate over the plane. So,
why A gonna be downwards?
Because I close it upwards. That's a good question. I close it upwards, so
Like half a sphere.
yeah. This is this awful painting. It's a kippa. We have in Bar-Ilan. Half a sphere, then a plane. I could have done it the opposite. If I did the opposite? I would switch the dA pointing upwards. That would give me the force on this charge. Now I'm calculating the force on this one, but of course in this particular problem, it's exactly the same. Maybe I'll comment about this a bit later, but now I'm going to write this as T times dA. And I need to integrate. So, of course, the math, we already looked at this. I'm not going to repeat this. What is T dot dA? But this is this matrix. The point now here is this is in z direction. Hence, only these elements are important. Tzx, Tzy, Tzz. Of course, I could calculate this with a more complicated structure. This plane is just a theoretical one, and then I'll have something else. But in this choice of the surface, only these 3 are important. And luckily, because it's a simple problem, 2 of them are 0, so I'm left only with Tzz, and that's it. Okay, so we can calculate this. This is integration over the area. And the area is this half sphere. Okay, so let us do this. We have Tzz, we have dAx. Okay, dAx I'm going to write down. So this is E0 divided by 2. I'm just copying from here. Q 4 pi epsilon 0 squared. Minus 4, because we have 2 of these guys. Integral from 0 to 2 pi. This is the integration inside the plane over the angle phi. dr r. Here I have r squared r squared plus a squared to the power 3. And then the most important part from my point of view is the minus 1. This minus 1 comes from the direction dA is in the minus dA z direction. It's in the minus sign. So this is important. This is what I mentioned before. If I had, if I would close it differently, it would be different. But this minus is important. Now, okay, so here this is integral from 0 to infinity. Now I need to do an integral. I can write down the relevant integral. I hope you all see that this guy, together with this guy, is the area. So in a plane, this is r dr, and this is here d phi, and this is this small area here, d phi r dr, which is the dA. This is something that I think, again, you are familiar with. So now there is an integral here. This integral is not difficult. You look up a table of integrals, I'll give you the integral. What is the integral? Yeah, this integral is what you need to solve with y to the power 3, because you have r and r squared, and then you need to plug this one, y plus y squared to the power 3 dy. This one is 1 over 4. You plug it into chat and you'll get this answer, I think, or Mathematica.
למה הוא בחזקת... כי שם...
What I do is I take the A, the A here, this not to be confused with this A here, very bad choice. The A here is the distance to the charge, and this is nothing to do with area, bad notation, this should be D. And again, this comes from the Coulomb's law plus the cosine of the angle 90 minus alpha. Then I have to square it because I have these squares here. And then I get this integral. So happens, yes.
Why does that TZZ have the minus 4?
That's a good question. ZZ has a minus 4. Yeah, this one is 0, minus minus. I think that's the answer.
Okay.
Because EX squared is obviously positive, EY is obviously positive. When you square things, they are positive, and then minus. So there's no problem. It should be minus for sure. If EZ is a 0, then this is negative. Is your question mathematical or physical? I mean, yeah, so then it's trivial because of this, unless you disagree with this definition, which is simply this definition. This is this minus sign. You see here, if I'm talking ZZ, so you have the X and the Y in ZZ will be with a minus sign, and this is these minus, minus, and then minus. Okay, so everything is okay. So I find this FZ eventually. If I use this integral, I'm not going to do this. I get what I expect. Okay, there's no surprises here. Integral over 2 phi, I'm just going to write the answer. Is q squared 4 pi epsilon 0 1 over 2a squared, as expected. As we know from Coulomb's law, 2a is the distance between the two charges, and we got what we expected. Now we can ask, maybe following that, the question that we had here, let's say we had a different problem. I'm not going to solve this problem, but let's say we had a problem like this. What will change? I mean, this one is q, and let's say this is 2q. Now, what is maybe confusing, maybe not, I have here in this plane some t, something, right? Some t. that you can calculate. It's not so difficult. Now I want to calculate the force on this charge or the force on this one. What do I do to calculate the force on this charge? I close from the top and I integrate. But let's say when I close it here, it's 0. I do the integration. But when I close it here, the remaining integral also here is 0. So what am I integrating over? Only the t in this plane. So now, it's not a complicated question. I'm not tricking you. Why is the force on this one and this one different? How will this pop up? Because I'm integrating over the t in this plane. It looks like they're the same, right? The same integrals, naively, but they are not, of course, because the forces are different. That's related also, I think, to your question. So what's the answer? I want to go and party, that's the answer.
אני לא בטוח שצריך להיות שם כאילו 4, כי אתה כאילו...
That's a different question, but...
לא, זה קשור לזה לדעתי.
No.
כי זה אמור להיות מטען אחד, ואז זה הסיבה.
No. This is important and you're absolutely wrong. The stress transfer, you are thinking like this, it's a good thought, and I'm sure Maxwell had the same thought at the beginning. When you calculate the stress transfer, you're calculating the force. We should ignore the charge that you are acting with the force on itself because I'm putting myself. But the answer is no. You are just calculating the charge, the real electromagnetic field, and you're doing this integral. So thank you for asking this question. We should have mentioned this before, but no, this is just, in all these equations, these are just electromagnetic fields somehow created in space and time in principle. We don't care what are the sources. That's actually the beauty of Maxwell. You don't, if it would be like you, let's say I want to calculate here on this charge, but I didn't know that it exists here, so how would I subtract this electromagnetic field created by this one? I don't know. I just measure this electromagnetic field and that's it. That's the beauty of Maxwell, actually, one of the beauties. Okay, back to this question, 2 charges. So the answer is the following. What will change? If I have 2 charges, then I will not have this Ez will not be equal 0, right? Because I'll break the symmetry. And if Ez is not equal 0, then I'll have additional terms. But again, all the matrix elements in the plane are the same. But what is the difference is that when I integrate with dA up or dA down, that will give you different results because of one of the terms. So you need one more. You need these terms not to be 0 in order to see a difference. In this problem, they are 0. They are cancelled, but in the other ones they will. So yeah. So the bottom line is that this sign that I had here, this -1 that I added here, and the directionality of dA can be very important, especially when you have more elements here. In this simple problem, when this is Q and Q, then this is not important. So the directionality is important, even though the T, the stress tensor itself, doesn't give direct information on the direction of the force. So okay, so that was a small comment. Now I'll also give a small comment, but which is actually a very big comment related to the question that was asked here, and maybe if you're more mathematical or in more advanced courses, you'll study this more. This will be very briefly. In this business, there is an issue with the reference frame, and there are all kinds of invariants. This is actually the reason why we call this stress tensor a tensor and not a matrix. So one of the invariants that you can prove, okay, what do I mean by invariants? I mean, invariants are objects that are insensitive to the reference frame. And again, the T itself, the elements in T are sensitive. So a mild definition of a tensor is the following. A tensor, unlike a general matrix, is a geometric object that has a meaning. I'm not saying what is the meaning. independent of the reference frame. What do I mean has a meaning? It's very vague. It means that if I will calculate this f with one choice of reference frame and this f with another choice of reference frame, the answer eventually in the same physical direction will be the same. That's what it means. The elements are the same. And then there are all kinds of invariants, and one of them is the trace of the trace of the tensor. So what is the trace of this tensor? This is txx plus tyy plus tzz. Let's say, for the sake of simplicity, I always like to do this. B is equal 0, so we have only electric field, so I don't need to add up also the magnetic field. It's super easy from here. You see, you have here only, when I and j are the same, you have here only ex squared, ey squared, ez squared. I think you can see it from here. And then when I'll sum them up, I'll just get squares of ex squared, ey squared, ez squared. And this is simply easily proven, 1 over half epsilon 0 e squared. Now this has a meaning, which is, I don't know if it's surprising or not. What is this e squared? This is the energy density up to a sign. This is the energy density at this specific spot in space. Energy density that comes from the electric field, and then if you add the magnetic field, it will be other thing. Now, this is invariant under a change of reference frame. This is pretty obvious, but let us just give you the simplest example. Let's say in one reference frame, E is E0 in the z direction. X, Y, Z. So the trace of T is simply 1/2 epsilon 0 E0 squared. Now I choose a different reference frame. I choose it like this. I hope you understand what I'm plotting here. This is x prime. So the z prime is going inside. This is the right-hand notation. X cross y, z is inside the board. So in this reference frame, let's call it E prime, I'm using, of course, the same field. I mean, the field has a real direction, right? So in this reference frame, this is E0 in the x prime direction. And then what is the trace of T here? It's 1 minus half epsilon 0 squared. Independent of the choice of the reference frame, the trace is the same in this example, but it's much more general than these two simple examples. I just plotted this here in order for you to have a feeling for this. There are other invariants, but he asked me how many invariants are there. I actually don't know. I asked someone, but he also didn't know. So there are two professors who don't know. And this is someone who teaches this course. So, okay, so I don't know. I asked ChatGPT, he didn't answer me. It was very complicated. I don't know how many invariants, and maybe it's even not a well-defined question. I'm not sure. Maybe there are infinite of them. I don't know. But another invariant is, you can show, for example, what about the eigenvalues? So we have this tensor. The tensor is a matrix. It's a real matrix, and it's a symmetric matrix. In quantum mechanics, we call it Hermitian matrix. But Hermitian is more general because it can have complex values. What does it mean, the eigenvalues of T? So we know that eigenvalues of T, they are real. And we also know that t, we can diagonalize it. And diagonalizing t might sound at first very good thing. Let's diagonalize it. Then we will not have these off-diagonal terms. It sounds good. But it's not so practical in the following sense, because it's local diagonalization, because the stress tensor depends on x, y, z, and t. So if you go in one x, you have one diagonalization, and another x, different diagonalization. So usually we can diagonalize it locally easily, but it's more complicated than you can imagine. But in principle, you can diagonalize it, and then you have only pressures and no shears, because there is a simple direction. And there's a unique direction, if you want, where unique direction where it's diagonal, and then there is no off-diagonal terms. Sounds good, right? And in this case, what you care about is the eigenvalues, because in the diagonal matrix, the eigenvalues will be on the diagonal, right? So another invariant is the following. The eigenvalues of t are real, but they are also invariant. So you can calculate these eigenvalues in different reference frames. One of them is the diagonal reference frame, and they will give you the same answers. It doesn't matter. And of course, the sum of the eigenvalues is the trace. So there are all kinds of invariants of this tensor, just implying, the message is very simple, that this tensor is more than a matrix. That's what I want to convey to you. It has very nice transformation methods, transformation properties, invariant for the size of the system. So, I'm sorry, but just briefly, I want to introduce the next lesson, because that will be a terribly long lesson. So I'll just give some motivation, and then I'll release you, hopefully quickly. That's what we're going to do in next class, so maybe this will convince you to read. So now we're going to leave these stress tensors aside, and we are going to deal from now to the end of the class to many types of relativistic effects. So potentials and fields. This is chapter 10 that you're going to read. And now I just want to explain what are some problems in the way you think about things up to now. So I'll do this with an example. So let us say you have an infinite plane. Now this is a real plane with a current density, and it's in, this one is denoted with what? It's not J, it is K. And this is Q, the units are Q time L. So if I have here some L, if I multiply Q by L and I measure for a few seconds, this will give you the total. So the total number of the total charge going through this element here. So this is K, like in J. We had it in the previously, but I want to remind you what is K. So this in static problem is a well-known problem, right? If it's fixed. But let us now think about what happens if, let us assume that K, this is, by the way, this is the x direction. I define this as x direction. So let us assume that K now is depending on time, and it is the following. It's K0, let's call this K0, which means constant, independent of time and independent of space, for t equals 0, t less than 0. What does it mean? It's very simple. I have a sheet. At time t equals 0, I switch on the current. This is the start time of the experiment. Every experimentalist will turn on the current in his sheet, or her sheet, right? Maybe he appeared 200 years ago, but he turned it on one time. Now we want to think about, let's say, start with the magnetic field in this object. So let us think first on what you know, and that is the static field. You know how to solve this. You solve it with Ampere law. You create this loop, BDL is equal I enclosed into this loop. This loop has a length L. The L will fall down. And this is a problem that you solved I don't know how many times. But this B in the static limit is U0 K in the y direction divided by 2. This is for z greater than 0, and then minus u k y over 2 in z less than 0. So you have a field up here in the y direction. This is the z direction going up. You know these directions because this is the right hand notation. So if I take, this is the plane, this is the right hand.
It needs the minus.
Up here in the z greater than 0?
Yeah.
I don't think so, but it's not so important. What is important here is plus and minus. Why do you say that? Because
x is here, so y
x,
is
z, x, y, you're right, x, y, z. Yeah, maybe I missed up this one and this one. This is what you say. Thanks. So this is this field. But now comes my point. Sorry for this bit. I just wanted to say what you know, and I made a mistake. Okay, so this is the field. I think you all know this. And now let's just think about this field, and this is my introduction to the next lesson. Does this make sense? Or there is a severe limitation on this in the context that, oh, okay, at some time in history I turned on the field. Where is this not valid? What? Yes, so there is a problem here in the fact that the speed of light is finite. So if I'm in z, so this is my plane, and then I go up here, and if this is c times t, again, t equals 0 is when I turn on the field, then I expect b to be 0 up here. And here b is not equal 0. So what we get, and this you can show from Maxwell equation, is that b is equal 0 for z in absolute value bigger than ct. But we will show how to get it in the next lesson. We are not showing this right now, but this is very physical, and meaning that there are limitations on the static approximation in the following sense. Let's say I switched on the field 2 years ago. Still very far away, you are not reaching the static limit, right? Because, okay, let's say this will be 1 year. The light will go very far away, but there, very far away, you will see the switching on of the field that happened 1 year ago, and you are not reaching there, you are not reaching the static limit. Maybe in the vicinity of this object you are, but not far away. Okay, so there's no static limit. And this thing becomes even worse when you talk about the electric field. So now, the magnetic field, as a function of z, I'm telling you, but I'm not proving, is a constant. This is b in absolute value. The direction is y. The value is this value. This is ct1, and then if I go to longer times, it's a constant, and then this is ct2. So as I go on and on, you'll have, this is again z. This is, let's say, above the plane. You have some magnetic field, but this is the front. This is the wave front, if you want, which is sharp here, that is propagating, and we need to take into consideration in again, chapter 10. But what does this mean? What does this mean on the electric field? We have here a current. There's no charges here. But this means if the magnetic field is changing here, it's not a constant, there is a magnetic flux. So there must be also an electric field. It's not just a static field. Again, this comes out from which law? I think you all know this. So, okay, let's write down the B. The B is this minus, I think this is a mistake. Okay, this is Z less than 0. U0, K, M over 2, theta, Z less than CT. That's the new thing in the Y direction. What is theta Z minus CT, less than CT? This is 1 if this condition is held, and it's 0 otherwise. So this is a step function. It's called a heavy step function. So theta condition is 1 if condition is true. Okay, so what is the electric field in this example? How do I calculate it? So let us now redefine the whole problem. Let us say that somehow someone created this magnetic field. I'm not asking what are the source. I told you what is the source. This is this K0. Given this magnetic field, I can calculate the electric field. I don't need to be in this problem, at least you can calculate easily the magnetic field, the electric field. And this is simply given by the Faraday law. Okay, so this is X, Y, Z, ddx, ddy, ddz. Okay, so maybe I'll simply give you the answer. So again, I'm not proving this, but you can check that it is consistent. This is going to be okay. This is going to be the electric field that you can calculate. I'm not showing you why, but you can calculate from the from Mr. Yeah, B. Yeah. No, this is okay. Minus dB dt. This is only in the y direction. So what happens here, these guys go away. And I'm not showing, but the derivatives of z and the derivative of t of the theta function, they give you delta functions. There's a bit tricky there, and then you can show that this is the electric field. But this electric field is actually very, very strange. Why? Because what is the relation between... okay, what is not so strange? First of all, E is perpendicular to B. This is something that we had already in the class when we looked at waves, right? That E and B are perpendicular one to another. We also see, because of the C is the speed of light, that the ratio between E and B is given by the C. This was also known previously when we studied free waves. But what is really strange about this is that when you look at it, is that in the static limit you expect E to always be there. But in the static limit we don't have an E in real systems. So what is actually happening here is the following. What is the physics here? Why E exists and why there's no static limit which says E is equal 0? Remember, if I have only J and I just do statics, there is no E. There's just B. But here it's the same like as B and the E exist. What is going on here? What was maybe wrong with statics? You can say it's not exactly wrong, but it's the following thing. And this is something deep. What is going on here? We have the plane. And we have here this current that was switched on at time 0. And let's say I have a point here. And I want to calculate the electric field on this point. What is going to influence this point? Let us look here. Can you send information from this point to this point? The answer is it depends how far, what is the distance? Is this distance shorter or bigger than speed of light times t, right? So if this distance is shorter than ct, this current here can influence this point. But if, let's say you are here, so let's say this distance, let's call it, how do you want to call it, d. This is d is, let's say, less than ct, this d is bigger than ct. This point here, which is on the plane, is not important. So what is happening here? As time goes by, more information is transmitted here. So you make it larger and larger and larger, and when you increase time, more information is given. And if this plane is infinite, there will be always new sources for the electromagnetic fields here. If this plate is finite, L by L, and Ct is much bigger than L, then this is not a problem. You can reach a static limit. But if this plane is infinite, for every moment of time you add some source, so to say, that is starting to influence it only after some time. And that means that, what does this mean from point of view of physics? If I want to think about this as some force acting on this point, usually when you think about forces, let's say between two charges, what is the force? It's the force coming from here to here. How long did it take it to travel? Immediately. That's the usual Coulomb force thing that you think about, or never mind, it comes from a J, comes from a rho, it doesn't matter, it's immediate. But here, no, it depends how long it took him to arrive at this point. So this means that the forces effectively are related to something which are related to the past history, to memory, to what we call, or everyone calls, retarded potentials. What is the word retarded potentials? It's not that they are stupid, retarded people. Retarded means retarded in time, that some event in the past influences the present. That is the retarded potentials, the both A and B, that are in this chapter, and this is what we are going to learn. We need to have this causality into the theory, and this is a big step, because forces are not anymore, or fields, or whatever you want to call them, are not transmitted immediately at the instant of time. The memory, at least in an infinite system, when you turn on the field, remains forever for certain observables. Again, it doesn't imply that magnetostatic is wrong. It implies that we need to be very careful. If speed of light would be infinity, all this will not be important, but speed of light is finite. Okay, so now you want to go to hear something in the speed of sound. So again, I apologize for taking your time, but it was important, so thank you very much.
Thank you.
Thank you.